go. And so we're going to talk about three-phase systems. In general, three-phase equipment is more economical. We've talked about that a bunch of times. More efficient than single-phase. We've talked about that several times already. And the main thing we want to talk about is examples. And I've got to warn you that Singer uses V for voltage instead of E for voltage. And so anytime we see V, we will write E, right? Okay, so if a three-phase Y-connected generator delivers 120 volts per, where's the rest of the question? Okay, what is the line voltage? If it's delivering a Y, remember that a Y, the voltage difference between the phase and the line is the square root of 3 times the phase is the line. And apparently we're missing part of the question, but that's okay. 120 volts per phase, I think it's saying. So we're going to multiply that times 1.7321, and we're going to get 208 volts. Okay, so a three-phase Y that's 1 and 20 on the phase is 208 on the line. From line to line is 208. Three-phase Y-connected generator has a terminal voltage of 480 volts and delivers a full load current of 300 amps. So let's look at this full load current per phase. Find the full load per phase. The phase voltage. So when it says find the phase voltage, what is it telling us when they call it the terminal voltage of 480 volts? Is that a line voltage? And then the KVA rating and the full load power in kW. So then that's talking about true power, right? So now we're talking about triangles, yes?
Yeah.
Okay, that's possible. Let's look at the next slide. And the solution is, in a Y-connected system, I'm thinking that phase current is equal to line current. And that's true. Phase current and line current in a Y are the same. It's really hard for me to see V, and that's confusing. I know that's easier for a lot of people, but phase voltage is equal to line voltage divided by 3, square root of 3, I should say, which is kind of saying it backwards. I don't like doing it backwards like that because if you remember one of the formulas, remember that phase voltage in a Y times square root of 3 is line voltage. You can remember that, right? And then the other one is going to be line current in a delta is equal to the phase current times square root of 3, right? So if you just remember those two, you don't have to remember this thing divided by that thing, because if you know that in a Y, the phase voltage is square root of 3 times line voltage. So if we move that around, we get this formula right here where phase voltage is line voltage divided by square root of 3. We just do the algebra to find it there. We'll find that 480 divided by square root of 3 times is divided by 480 is 277, right? Is that correct? Okay.
Yeah, 277.
All right. And then part B of this question is, or part C, that is part B. Oh, the currents are the same. Why are we dropping out? Don't do that. Got to fix that. That's good. So anyway, the first question was, what was the line current, I think, and we had the phase current. The second question is, what was the phase voltage? And we found that's 277. And our power, our input power, We know that the formula for input apparent power is just if we have the phases, then we can just multiply the three of them together, multiply the phase voltage times the line, phase voltage times the phase current times 3, and we'll get the total apparent power. Where we need the power, we need the cosine of the angle, okay? Because we need the power factor times that. So our apparent power, our VAs, is 277. No, it's times 480. So we have a really high voltage here. I think they made a mistake. Oh, the kVA is square root of 3. They're using line total. Square root of 3 times 480, which is the line voltage times the line current. The line current is 300, and they want to turn that into kVA. So to turn it into kVA, we have to divide by 1,000. And so we see that square root of 3 times 480, which is the line voltage, times 300, which is the line current, will give us 2, and then divide by 1,000 to get the kVA, we'll get 249.4 kVA. Our power, oh, that's really annoying. I've got to. Our power, I don't know where we got the information that we have an 80% efficient system. I don't remember that from the previous slide, do you? It doesn't say it's an 80% efficient motor or load, but that's okay. So we would take line voltage times square root of 3 times line current and multiply that times the power factor. And in this case, we're given 0.8, and then divide that to get it in kilowatts. And our answer isn't given. Gotta love that.
I've got 16,588.
Well, if our apparent power was 249, it's unlikely that our true power, forgot to divide by 1,000, I think. You did? Okay. 1.7321 times 480 times 300 times 0.8 divided by 1,000. 890? That's not possible. I'm not sure how, though.
That's 3 different numbers. That's wrong.
Times 480. Okay, so if we multiply out 1.7321 times 480 times 300 times 80%, all divided by 1,000, we'll get 199. Is that correct?
That's what it said before.
Okay. So we get 199 watts, kilowatts, I should say.
199.
Okay. Let's take a look at another example. We have a 220 volt three-phase induction motor, and it draws a full load current of, why am I thinking that we're losing part of the slide? I think we are. The kVA input, find the kVA input, the kW input, and the full load power factor is 80%. Okay, so our apparent power, if we have 220 volt three-phase induction motor and it draws full load current of, it doesn't tell us what. It's going to be more difficult to figure out, I'm thinking. It must draw 35 amps. Okay, so we're doing this in what? We're doing this in phase. Now we're doing this in line also. 220 volts is our line voltage. 35 amps is our line current. So we're going to multiply square root of 3 times 220 times 35 and that would be 13,340 or thereabouts. And so we would wind up with dividing that by 1,000 to get 13.34 kVA. And our power, we're just going to multiply that times 80%. That'll give us 10.67 kW. And they've made a mistake down here. They're saying square root of 3 times. This symbol is not what's going on. This symbol's not interpreting from one. I'm taking information from one program, putting it in another, and it's misinterpreted in the translation. So that's supposed to be square root of 3 times line current and times line voltage. Okay. A three-phase Y-connected generator delivers 110 volts per phase. What is the line voltage between any two phases? So if simple question is saying in a Y-connected generator that has 120 volts per phase, we're going to multiply that times square root of 3, and that should come out to 190.5 volts. Is that correct? Okay, nice simple question there. Three-phase Y-connected generator has a terminal voltage of 350 volts and delivers a full load. I wish it told us the rest of the slide. I can do. Pause this. Okay, so this is the original slide from that I was trying to use in the notebook, but it's not working out, so we'll just write off the slide presentation. And a three-phase Y-connected generator has a terminal voltage of 480 volts, delivers a full load current of 300 amps per terminal at the power factor of 80%. A lot more information in this slide than the one that was in the notebook. Okay, so again, 480 volts, they mean that is the line voltage. So if we want to find the full load current, what are we talking about? We're talking about a Y-connected generator. If it's Y-connected, then the full load current per phase is the same as the full load current per line, right? In a Y, phase and line current are the same, which is what our slide right here says. In a Y-connected system, phase current is equal to line current. So phase current must be 300 amps. Okay, then it says, what is the total power? No, what is the phase voltage? So phase voltage, if we have the line voltage in a Y, then we can divide that by square root of 3 and get our voltage, which in this case is 277 volts. 480 divided by square root of 3, 277. Now it says, what is our apparent power? And now you know that we're doing line totals, we use square root of 3 times the phase current times the phase voltage gives us the apparent power, right? Okay, so square root of 3 times 480 times 300, and that'll give us our apparent power. And to turn it into proper engineering notation, we're going to divide by 1,000 to get 249.4 kVA. Knowing that that is our apparent power, if we have the power factor of 80%, we can just multiply that times 80%, and that is our true power, or 199.5 kW. Okay, next example, 220 volt three-phase induction motor. This is right down our alley. This is what we do for a living, right? 220 volt three-phase induction motor draws a full load current of 35 amps per terminal. In other words, each phase when Y connected. Find the kVA input, the kW input, and the full load power factor if the full load power factor is 80%. Okay, let's go down to our solutions. And the first question is, what is the kVA input? What is our power input? And our power input is square root of 3 times the line line voltage times the line current. And if we want to turn that into proper engine notation, we'll divide that by 1,000. So we have 1.7321 divided by times 220 times 35, and then we're going to divide that by 1,000 to get 13.34. Get our true power, we just multiply times 80% again, and we would find 10.67 kW. Okay. I don't know how they call that a quiz, but okay. The three-phase Y-connected generator delivers 110 volts per phase. What is the line voltage between any two phases? Well, that's really easy. If the line voltage in a Y is 110, we're going to multiply that times on square root of 3, right? Which will give us 190.5. Is that correct?
Yep.
Not much of a quiz if you ask me, but okay. And it says three-phase Y-connected generator has a terminal voltage, and we know that's line voltage, of 350 volts. It delivers a full load current of 200 amps per terminal at a power factor of 90%. Find the full load current per phase. Okay, how would we find the full load current per phase? We want the phase voltage divided by, no? How would we find the full load current per phase? It says the full load current of 200 amps per terminal at 90%. Are they calling 200 amp per terminal? No, that's phase current, right?
Yep. Phase and line.
Phase, oh, it's Y, so they're the same. Very good. Okay, the phase voltage, if we have 350 volts line voltage, then 350 divided by square root of 3 would be about 202. So our phase voltage is 202. The kVA rating, okay, we would take square root of 3 times our line voltage, which is 350, times 200, which is our current, and that would give us 121.2 kVA, our apparent power, and our true power coming out of this generator is 109 kW. Everybody agree with that? Everybody see the why? Pretty simple stuff so far, right? Okay. A 220 volt three-phase induction motor draws a full load current of 25 amps per terminal when Y connected. So 25 amps is our phase current and our line current, right? 220 volts three-phase induction motor means that that is the line voltage. Is that correct? So the kVA would be 220, the square root of 3, times 220, times 25, will give us about 9,530. Is that correct? Everybody hit clear, wait a minute. Everybody hit clear on your calculator. Okay, so what we really get is 9,526.55. If we round that, we can come up to their answer of 9.53 kVA. So now if we have 9,526.55 VA, we're going to multiply that times 90%, and we're going to wind up somewhere around 8.57 kW. Is that correct? All right.
Yeah.
Good deal. Okay. If the current Okay, now we're going to talk about, oh, wait a minute, did I skip one? Nope. We're going to talk about delta now. Delta connection. Now, what is the same in delta? Voltage is all equal, right? Line voltage is equal to phase voltage. But the currents are different. The phase current times square root of 3 is the line current. So it says here, if the current through each phase of a delta connected generator is 30 amps, what is the total line current? That's easy. We just multiply 30 times 1.7321 and we get about 52 amps. Everybody go along with that?
50.
30 times square root of 3. 1.732 times 30 is about 52. Okay. Each phase of the three-phase delta-connected generator supplies a full load current of 50 amps at a voltage of 220 volts and a power factor 80% lagging. Okay, we're talking about a generator. It's putting power out. What is the line voltage? Didn't it just tell us that? Each phase of a delta-connected generator supplies a full load current of 50 amps. What's all the same in delta? Voltage, but the current's not. So the line, the first question was what's the voltage, and all the voltages are the same. And if it's 220 on the phase, it's 220 on the line. So our first answer is 220 volts. And if we want to find the line current, it's given us a phase current, is that correct?
Yep.
A full load current of 50 amps. No. I think that is the line current. Full load current of 50 amps. That should be the line current. No, it's saying it's a phase. Oh, each phase, I'm sorry, each phase of a three-phase delta connected has 50 amps. So that's a phase current. So if the phase current is 50 amps, we multiply that times 1.7321, find the line current. So let's go down to the next one. So square root of 3 times the line current of 50 amps gives us 86.6 amps. It's our line current. And what is our total power? The total apparent power is square root of 3 times the line voltage times the line current. And then we're going to put it in proper engineering notation by dividing out by 1,000. So 1.732 times 220 times 86.6 is what?
Do I have to divide that by 1,000?
No, not yet.
Not yet? Okay, then that's 32,998.0.
32,900, we're going to round that to about 33 kVA. Is that correct? But before we round anything, let's multiply times 80%, which is our power factor, to get a correct power factor. I can get a correct true power. What is our true power?
41,247.
No. You divide.
Divided?
Why did you divide by 0.8? Multiply times 0.8.
Okay.
I can tell.
That's got to be what's wrong, yeah.
Yeah, no kidding.
Okay, multiply. 32,998.
No. 32,000 is what you had to begin with. You just got back to your base. 32,900. That is your true power. Don't clear it. Just multiply times 8 again.
Oh, I did clear it though.
Okay.
I can get back.
We wind up with 26,399. 26,399. We're going to round it. They're going to round to 26,000. Down this thing.
So I got the 32,000.
26,399, and they're going to round to 26. Okay. Okay. Let's go to another problem. Each phase of a balanced delta connected load consists of resistors of 56 ohm in series with a pure inductive reactance of 33 ohms. Oh my God, we have a angle problem here. The load is supplied with a 220 volt, 60 hertz three-phase line. So 220 is the line, it's a delta going in, right? Delta connected load consists of 56 ohms in series. And I don't like the next slide. So what I'm going to do is we're going to get creative and see how this works out. And see what happens next. Okay, so everybody okay with that so far?
So far.
Now, what do we have here? We have power triangle, right? No, we have, first we have to have, says it's got a reactance, inductive reactance of 33 ohms. Okay? And we also have a resistance of 56 ohms, right? We need to find the impedance of the circuit, right? What function do we have here before our very eyes?
Tangent.
Tangent. So now we're going to go second function tangent, 33 divided by 56, right? And we find out
30.5103.
so the angle is what? 5.1
Degrees.
Okay. Now, we need to find the hypotenuse, right? So let's take the cosine of that angle and just hit cosine, second function answer. And we find that the cosine of theta is what?
0.86153.
0.8651?
153.
153. 86153?
Yep.
Okay. So, we know that the cosine is what? A over H, right? We're looking for H, but we have A, right? So let's take, what happened there? Where'd my layers go? No! That was not nice. I guess the disadvantage of working with okay. Now delta load. Well, let's start over again. We've got a delta load. Is this the same problem?
Mm-hmm.
Yep,
Same problem.
okay. We got a triangle here. And we had 33 and we had 56 ohms and we had an angle.
Theta was 30.51023 degrees.
30.51023.
51023.
Okay, and the cosine of the angle.
186.
Eight, 6, 1, 0, 8.86153. 53, and that's equal to A over H, right? And our A is 56. We're going to divide 56. We're going to exchange these two. we're going to wind up with H is equal to 56 divided by 0.86153, right? And if we divide, now 0.86153 is in our calculator, right?
Yep.
So all we're going to do is put in 56 divided by second function answer.
65.
So we find that our H is 65 even,
Yep.
right on the money. Amazing, I tell you.
Are those volt amps or just volts?
That's VA.
Volt amps.
No, that's ohms. That's your impedance, your total impedance. That's this answer right here, 65 ohms. Okay, so what's the power factor? We multiply the cosine of the angle by 100, and we get 86.15%. Okay? What's our phase voltage? Okay? This is a delta, so I don't care which one it told us, 220 volts, whether it's a line or the phase. In a delta, they're the same, right? So we're going to say the phase voltage is 220 volts. What's the phase current? Okay? How would we find the phase current? If we work in phases, we can do that. Do we have the phase voltage? We have our impedance, right? Well, if our impedance is, let's see, delta connected load consists of, okay, so we can divide 220 by 65, can't we? Do we have any of those numbers in our calculator right now?
65.
We have 65, so we're just going to put in 220 divided by second function answer, saving a step, and we get the current of
3.384. Anybody else?
3 point what?
384.
Okay, so 3 point, why do we need the phase current? Because if we're going to divide, we have to have the phases. Okay, the line current. Now, if we know the phase current in a delta, which is 3.89, we multiply times the square root of 3, so now we have 3.89 in our calculator. We're going to multiply times the square root of 3.
That's wrong.
What?
Current is 3.384.
3.38.
Mm-hmm. I just rounded it off to 3.9. And I think that's huge when I said it.
3.38. Okay. All right, let's go back a little bit. That's, oh shoot! Don't drop everything out, please. You got to be careful with this board. Tell me it didn't drop everything out.
I can't tell you that.
It sure did. Okay. Is this the same problem? Great.
It's not even the same program.
Oh, yes, it is. Just the wrong slide. I can't believe it. Dumped all my writing. Oh no! That's okay though. We'll just go to the next slide. And it's going to do it by Pythagorean theorem, which you know I hate to do. But it did find that 0.862 is the correct phase angle. And 220 volts is the phase voltage. We find all these same things. Let's see. It found the true, okay, 3.38, so it actually found the same voltage we found. phase current is equal to voltage divided, phase voltage divided by the impedance. And so we have 3.38. So we're going to plug that in and multiply that times square root of 3 to get our line current. Okay, and if they're going to find the power, they're going to do it with line current and line voltage, and our line current is 220, line voltage is 220 volts, and our line current is 5.85. Multiply that times square root of 3, that'll give us our total apparent power, right? So let's multiply square root of 3 times 220 times 5.85. What is our total apparent power? Right here it is, 2.23 kVA. Is that correct? They rounded a little bit, didn't they?
Yeah, they rounded.
Okay, but that's okay. Times 0.862, which is our phase angle, times 100%, or that's just our phase cosine of our angle, 0.862, and then divide by 1,000 to put it in proper engineering notation. We find that we have 1.92 kW. I think that you should always find this one first instead of trying to find this one first and then come down and find that. That's logical, if you ask me. Okay, a three-phase induction motor draws 35 kW from a 220 volt main. Okay, what is it telling us? What is 35 kW? What are they telling us right here? That's watts. They're telling us that it has drawing a certain amount of true power from a 240 volt main. Is that 220 volt? Is that a line voltage or a line voltage or phase voltage?
On the main side, I would think it's
That would be a
Line voltage. That's a line. They're giving us a line voltage. And at 100 amps, if the line current is 100 amps, okay, it doesn't tell us whether this is a delta or a Y, does it? Y, motors are generally speaking a Y. Let's make sure by looking at what they've done here. And let's look at, they've used the square root of 3 times the line voltage times the line current, and they're plugging in 220 and 100, saying that that's a line total, okay? Sometimes these things are a little ambiguous, and singers, that's my only minor issue with them, if they're not clear on what this is sometimes. So this is a line voltage, right? And a line current. So line voltage, line current, times square root of 3 will give us our total three-phase power, right? What's 220 times 100 times square root of 3?
I've got 38,106.2.
Now, if we're going to turn that into proper engineering notation, we'll probably say that is 38.1 kVA, right?
Yep.
And what is it says? What is the power factor? Well, if this is our kVA, what are we finding here? And we have 35. That can't be right. Three-phase induction motor draws 35 kW. Oh, I put that in the wrong place, haven't I? 38,106.2. And let me see what happens here. Well, that really sucks. It even started switching programs around. Why is it doing that? Okay. Go back to drawing. Is this the same problem? Yep, okay. Have our triangle here. It was just trying to help me because I had made a mistake, right? 35,000 watts. And what was our apparent power?
38.106.
Not point. 38,106.2. Okay, so now what function do we have? We have the cosine, right?
Yep.
If we just divide 35, we've got 38,106.2 in our calculator, is that correct?
Yes.
Okay, so divide that by, or just put in 35,000 divided by second function answer, and we'll find our cosine. What? I wouldn't.
You want my number?
Yeah?
I've got 1,088.7.
1,000. That doesn't sound right. That can't be right. Oh, now it's going to bring back all my other numbers. Isn't that stuff? Stop it. All righty. Well, let's see what I can do here.
38,106 divided by 35. Is that right?
Something like that.
Or should I hit cosine first? Is that what the problem is? Cosine. 38,106.
I'll get this thing right yet. Wait a minute. If we just divide,
I've got a different number now.
I've got the wrong number down here. Oh, I've got all kinds of numbers all over the place.
I got 0.988.
Okay. Everybody hit clear on your calculator, please. We're going to go right to the cosine. We're going to divide 35,000 by 38,106.2. So put in 35,000 divided by 38,106.2. And we're going to get the cosine because that's A over H, right? So that's our fraction. What is that? That's not 1,000 anything.
No, it's 0.09184H.
0.9?
Yep, 0.9.
Leave the whole number. It's just zero. Wait, stop. 0.9184.
91,848.
No, that's not what I have.
I don't want that. Okay. $38,106.2. I don't know why this is so hard. Not 0.0, it's 0.91. 0.91848. That's cosine of theta, right? Now, if we want to know the angle, and we might want to, we can say cosine second function answer, and it'll tell us that that's not right. Oh, second function cosine, 0.91848. Our angle's 23 degrees. .29 degrees. If that's the cosine, then to find the cosine, you just put second function cosine and put in the cosine that you know, and it'll tell you the angle. Okay? So the power factor of the motor is 91.84% or 85%. And the reactive kVA, okay, it's saying what is the side over here. So now we need the sine of this angle. Now, fortunately, we just found the angle, so we have 23.29 degrees in our calculator. Is that correct? Okay, now, all we have to do now is hit sine, second function answer, enter, and that will tell us the sine of this angle. What is the sine of this angle? Sine.
0.3954.
Well, I do, but okay. So we think that the sine of this angle is 0.3954, and if that's true, that is O divided by H. So we know the H is 38,000, so we're going to multiply 38,102.106.2 times 0.3954, which is the sine, and that'll leave us with the side opposite, which is our vars. So 38, now we have 39.54 in our calculators, is that correct? Okay, or just hit clear twice and put in 0.3954 times 38,106.2. We'll wind up with how many vars? What was it?
I'm having a new catch up.
Okay, we got about three different numbers.
67,29.
So it's 15,000. What? 067, thank you. That's vars. So 15 kVars. That didn't start recording yet, did it? All right, so we have one final problem. In each phase of a three-phase delta-connected generator, it supplies a full load current of 40 amps at a voltage of 220 volts and a power factor of 90% lagging. All right. Well, let's start writing on this slide again, because we have a phase angle problem, right? We want to find the line voltage, the line current. Okay. This is a delta. So what's all the same in delta? Voltage. So if we have a full load current of 220 volts, that means that the line current, the line voltage is 220 volts. So the line voltage is 220 volts. It's asking us what it's telling us. The line current, okay, is saying that the full load current is 40 amps. Oh, each phase, I'm sorry. But our line voltage is still, if this is a phase voltage, 220 volts, the phase voltage is 220 volts, and the line voltage is 220 volts. If the line current is 40 amps, we're going to divide by square root of 3 to get our phase current, right? So 40 divided by square root of 3, or 40 divided by 1.7321.
23.09.
They're saying multiply times square root of 3 because they're saying this is a phase. Oh, I'm sorry, this is a phase. My apologies. This is a phase current that's 40 amps, not a line. So we're going from 40, we're multiplying times square root of 3. So 40 times 1.7321 will get 69.3 amps, or somewhere close to that.
69.28.
Okay. And our full three-phase power Now let's do this with our phase currents because this is actually easier. Okay, we have our phase voltage, our phase current, right? 220 volts is our phase voltage, and our phase current is 40 amps. Everybody agree with that? And when we use phase totals, it's much easier. We just multiply times 3 instead of square root of 3 or something else. And so 3 times 220 times 40 is a nice even number, I bet. What is that?
26,400.
Amazing, I tell you. And as I said, we could do this with line currents and line voltages, but then we multiply times square root of 3. Now, if we know that we have 90% lagging power factor, then this times 0.9 is going to give us our true power, which is about 23.8.
About 23.8.
23.7 something, right?
76, yeah.
23.76 becomes rounded to 23.8 kW, sorry. All right. Well, that's the end of that for today.